This video demonstrates the Discover tool for detecting algorithmic complexity vulnerabilities in source and compiled Java bytecode applications. Algorithmic complexity vulnerabilities are vulnerabilities that enable denial-of-service attacks and typically stem from the asymmetric consumption of resources due to complex loop termination logic, recursion, or interactions with intensive library APIs. A well-cited example of an algorithmic complexity attack is the Billion Laughs XML bomb. By using XML entities, an attacker can craft a small input file that, when parsed by an XML parser, expands into a billion LOL strings concatenated together, which take up almost 3 gigabytes of memory. These types of vulnerabilities inspired DARPA to create the Space-Time Analysis for Cybersecurity program known as STACK. Let's take a look at how to detect an algorithmic complexity vulnerability on one of the released STACK challenge programs. We will use Discover to find the vulnerability in an application called GabFeed that causes the program to exceed its runtime limit of 5 minutes for a small input that is less than half a megabyte. The overt description of the GabFeed application is that it is a web forum server that allows users to post messages and search for posted messages related to special topics. Since we do not have access to the source code of the application, we will perform our analysis on the compiled Java bytecode. The code consists of more than 23,000 lines of bytecode when translated to the Jimple intermediate representation. Our analysis strategy will be to use Discover to automatically catalog and characterize all of the loops in the application. We will then iteratively filter the loops to loops that are likely to contain an exploitable algorithmic complexity vulnerability. Finally, we will perform an interactive audit of the loops identified to confirm our hypothesis of the vulnerability. We start by generating the loop catalog for all loops in the application. The loop catalog includes several properties of each loop. We will filter the loops first by loops that are reachable from attacker-controlled entry points in the application. Since we know that this is a web application and that the input must be received using a network API, we can further filter the identified loops to loops that make use of network APIs. Loops that are monotonic have simple termination logic and are not likely to contain an algorithmic complexity vulnerability, so we further filter the loops to non-monotonic loops. Finally, since many loops that are non-monotonic depend on APIs that have well-understood upper bounds, we can further restrict the loops to a set of complex loops without well-understood loop bounds. In the first filter, we reduced 112 loops to 75 loops influenced by the attacker. In the second filter, we reduced 75 loops to 35 loops that interact with network APIs. Of those 35 loops, 14 were non-monotonic loops, and 9 of those loops did not have well-understood loop termination patterns. Next, the analyst will interactively audit this manageable set of 9 loops. To keep the video brief, we will only show the audit of the loop with the vulnerability. We can use the interactive graph visualizations provided by Discover to view the loop body of the loop of interest. The loop termination projected control graph, or LPCG for short, is a compact representation of the relevant control flow within the loop that conveniently highlights the loop termination conditions, loop control variables, and call sites within the loop. In this example, the LPCG reveals the presence of a differential branch that creates asymmetry by guarding the only path to a function called merge helper. Since there is previously an unconditional merge before this merge operation, satisfying the condition would result in an expensive duplicate merge operation. The condition is satisfied if the number of messages is 8, so the analyst hypothesizes that the malicious input could be crafted to cause an expensive processing of posted forum messages. With some additional targeted dynamic analysis, this hypothesis was later confirmed to produce an algorithmic complexity attack using a small web request that causes the system to exceed its 5-minute runtime budget. Everything you have seen in this demo has been made open source under the MIT license. We invite you to try using Discover or help to extend this research in the future. Thank you for watching.